Welcome, stargazer, to the edge of understanding, where the known universe softens into shadow, and the laws of physics blur like starlight in a telescope's lens. If you've come here carrying the weight of daylight thoughts, the unfinished tasks, the unanswered questions, let them drift away now, like matter spiraling toward the event horizon, dissolving into the quiet. Tell us however long it usually takes you to drift off to sleep, whether minutes or hours, and where you are joining in from. Know that tonight time will stretch and bend like space-time near a black hole's event horizon, carrying you gently into rest. We don't journey to the moon, but beyond, into the velvet darkness where space and time curve into impossible shapes. This is not a story of human triumph, but of cosmic humility, not of light, but of the beautiful darkness that gives light its meaning. We'll wander the borderlands where reality bends, where a single cubic centimeter of space holds more mystery than all the libraries on Earth. Picture, if you will, the perfect silence inside a black hole's shadow. No wind, no echo, just the faint quantum whisper of particles dancing at the edge of oblivion. Imagine the last photon of light stretched to infinite redness as it struggles against gravity's embrace. Feel the strange comfort in knowing that even in this most destructive of cosmic phenomena, nothing is truly lost, only transformed, remembered, encoded in the holographic fabric of space-time itself. Before we cross this theoretical threshold together, I wonder, what does the word black hole conjure for you tonight? A cosmic vacuum cleaner? A celestial monster? Or perhaps something more poetic? The universe's way of folding in upon itself, like a thought too profound to speak out loud. However your mind envisions these gravitational mysteries, I invite you to release those preconceptions now as we prepare to explore the reality far stranger, far more beautiful than fiction. The equations on our screens are merely shadows cast by a deeper truth. The terrifying renderings in documentaries, mere approximations of phenomena no human eye will ever truly see. But here, in this quiet space between wakefulness and dreams, we can perceive them differently, not as destroyers, but as the universe's most careful archivists, not as endings, but as gateways to new physics, new understandings, new cosmic possibilities. So let's breathe together, in and out, and allow the boundaries between science and wonder to dissolve. Let the glow of your screen become the accretion disk's faint radiance, swirling at light's last possible orbit. We're about to contemplate a phenomenon where a teaspoon of matter could weigh as much as a mountain, where time slows to a standstill, and where the universe keeps perfect accounting of every atom that crosses the horizon. The mathematics is complex, but the essence is simple. Black holes are the universe thinking deeply about itself. And in this hour, we become the universe contemplating black holes in return, a perfect symmetry. Shall we begin our descent? Don't worry, no falling happens all at once. Like matter spiraling toward the event horizon, we'll approach gently, gradually, until the boundary between observer and observed begins to blur. The most profound darkness is not empty. It hums with quantum potential, vibrates with strings of energy too small to measure, warps under the weight of its own gravitational poetry, and it remembers, always remembers, every star it has ever swallowed. In the infinite velvet expanse of the cosmos, where galaxies swirl like dust motes caught in a sunbeam and nebula glow with the soft luminescence of forgotten dreams, there exists celestial phenomena so profound they challenge our very understanding of reality. Among these cosmic wonders, none captivate the imagination quite like black holes, those enigmatic architects of space-time where gravity grows so unimaginably strong that it warps the fabric of existence itself, creating bottomless wells from which nothing, not even light, can escape. Yet hidden within their inscrutable depths lies one nature's most exquisite paradoxes: the delicate interplay between these gravitational titans and the fleeting, ethereal world of quantum mechanics. This is the story of how black holes, those colossal manifestations of cosmic power, engage in a silent, eternal dance with the quantum realm, a dance that reveals the universe's deepest secrets in whispers almost too faint to hear. Picture yourself floating in the profound stillness of space, gazing toward the event horizon of a black hole. This boundary, the point of no return, is not the static wall it might appear to be, but rather a shimmering, dynamic surface where the laws of relativity and quantum mechanics meet in a breathtaking display of cosmic harmony. The space surrounding this horizon is far from empty. It thrums with latent energy, a quantum sea of potential where particles flicker into existence like fireflies in the night, only to vanish moments later. These are virtual particles, ephemeral pairs of matter and antimatter that emerge spontaneously from the quantum vacuum, borrowing energy from the universe itself in accordance with Heisenberg's uncertainty principle. Normally, these particle pairs annihilate each other almost instantly, returning their borrowed energy to the vacuum as quickly as it was taken. But near a black hole's event horizon, something extraordinary occurs. Gravity here is so intense that it can tear these particle pairs apart, sending one member spiraling irrevocably into the black hole's maw, while the other escapes into the cosmos, carrying with it a minuscule fragment of the black hole's energy. This slow, inexorable leakage of energy, Hawking radiation, as it was named after the visionary physicist Stephen Hawking, who first theorized its existence, means that black holes are not truly eternal. Over timescales so vast they dwarf human comprehension, black holes evaporate, dissipating like morning mist under the rising sun. For the smallest black holes, this evaporation could occur relatively quickly in cosmic terms, ending in a final, brilliant burst of gamma rays. For the supermassive black holes that anchor galaxies, the process would take longer than the current age of the universe itself. Yet, Hawking radiation is merely the overture to a far grander symphony. Black holes are not passive absorbers of matter and energy. They are dynamic entities that interact profoundly with the quantum world, challenging our understanding of information, entropy, and the very nature of space-time. They exist at the crossroads of the macroscopic and the microscopic, where the smooth, deterministic fabric of general relativity collides with the probabilistic, uncertain realm of quantum mechanics. This intersection is where the universe's greatest mysteries lie hidden, waiting to be uncovered by those who dare to ponder the deepest questions of existence. As we embark on this journey together, let us drift gently through these cosmic mysteries, exploring how black holes serve as bridges between the vast gravitational architecture of the cosmos and the shimmering, elusive domain of quantum particles. We will wander through the strange landscapes of event horizons and singularities, peer into the paradoxical nature of black hole information, and perhaps catch a fleeting glimpse of how these cosmic phenomena might one day reveal the unified theory that has eluded physicists for generations. So settle in and let your mind expand like the universe itself as we begin our exploration of how black holes, those silent sentinels of the void, weave the fabric of reality with threads both impossibly large and infinitesimally small. The story unfolds slowly, like the turning of distant galaxies, each revelation a gentle ripple in the vast ocean of space-time. Close your eyes if you wish, and let the cosmic currents carry you deeper into the mystery, where the quantum and the gravitational embrace in the darkness, and where the universe whispers its secrets to those who listen closely. As we drift closer to the black hole's event horizon, that intangible boundary between the known universe and the unknowable abyss, we encounter one of nature's most exquisite contradictions. Here, in this liminal space where gravity stretches time and warps dimensions, the orderly rules of Einstein's relativity collide with the chaotic uncertainty of quantum mechanics in a cosmic ballet that defies all conventional understanding. The event horizon is not merely a physical boundary, it is a philosophical frontier, a place where our deepest theories of reality begin to unravel like threads from an ancient tapestry, revealing glimpses of something far more profound beneath. Imagine, if you will, the last moments of a star collapsing into a black hole. As its outer layers are compressed beyond comprehension, the very atoms that once burned with stellar fury are crushed into a singularity, a point of infinite density where the known laws of physics simply cease to function. Yet surrounding this unfathomable nothingness is the event horizon, a sphere of perfect darkness that marks the point where escape becomes impossible. It is here, in this ghostly membrane between existence and oblivion, that the quantum world makes its presence known in the most unexpected ways. The vacuum of space near the horizon is alive with quantum fluctuations, particle pairs blinking in and out of existence in accordance with the uncertainty principle. Normally, these ephemeral particles would annihilate each other almost instantly, returning their borrowed energy to the universe as quickly as it was taken. But near a black hole's event horizon, the immense gravitational field can separate them, with one particle falling inward past the event horizon, while its counterpart escapes outward as Hawking radiation. This process, delicate as a spider's web trembling in the cosmic wind, carries profound implications. Each escaping particle carries away a minuscule amount of the black hole's mass, causing it to slowly evaporate over eons. Yet this evaporation presents us with a paradox that has puzzled physicists for decades: the black hole information paradox. According to quantum mechanics, information about the state of a system can never be truly lost. Every particle that fell into the black hole carried with it information about its properties: mass, spin, charge. If the black hole evaporates completely through Hawking radiation, which appears to be random and featureless, what becomes of all that information? Does it simply vanish from the universe, violating quantum theory's most sacred principles? Or is it somehow preserved in ways we don't yet understand? Some theorists suggest the information might be encoded in subtle correlations between the escaping Hawking particles, like a cosmic hologram where three-dimensional information is stored on a two-dimensional surface. Others propose that the event horizon itself acts as a firewall, a searing boundary of high-energy particles that scrambles and preserves information in ways that challenge our notions of space and time. The truth may lie in concepts we're only beginning to grasp, like quantum entanglement's role in connecting the interior and exterior of black holes through wormholes of unimaginable complexity. As we contemplate these mysteries, we begin to see black holes not as cosmic vacuums, but as laboratories of quantum gravity, natural experiments where the universe tests its most fundamental laws. Their event horizons shimmer with quantum potential. Their interiors may contain entire universes compressed into singularities, and their very existence forces us to reconsider what we mean by concepts as basic as time and space. In the gentle glow of Hawking radiation, in the subtle interplay of particles at the edge of oblivion, we find clues to a grander theory that might one day unite quantum mechanics with general relativity, a theory of everything written in the darkness between the stars. Let us linger here for a moment, at this threshold between knowing and mystery, where the quantum foam of virtual particles meets the crushing gravity of a black hole. The answers we seek may be hidden in the delicate balance between creation and annihilation, between the infinitely large and the infinitesimally small. As we continue our journey inward, toward the heart of the black hole itself, we carry with us these quantum whispers, hints of a deeper reality waiting to be uncovered in the silent depths of space-time. We enter a realm where the very concepts of space and time begin to lose their familiar meaning. The black hole's interior is not merely empty space, but a cascading waterfall of space-time itself, flowing inexorably toward the singularity at speeds approaching that of light. Here, in this strange inner sanctum, the universe reveals one of its most startling secrets: the holographic principle, which suggests that all the information describing three-dimensional reality inside the black hole may actually be encoded on its two-dimensional surface, like a cosmic butterfly pressed between the pages of space-time's book. The mathematics behind this revelation is as beautiful as it is counterintuitive. Just as a hologram can store a three-dimensional image on a flat surface, the physics of black holes suggests that all the information about every particle that ever fell into its depths, every atom of interstellar dust, every photon of starlight, perhaps even entire civilizations, might be perfectly preserved on the event horizon's surface. This surface, shimmering with quantum fluctuations, becomes a vast cosmic hard drive where bits of information are stored in Planck-sized pixels, the smallest units of meaningful space. Each bit corresponds to an area about 10 to the negative 35 meters squared, so small that a single square centimeter could contain more information than all the books ever written in human history. This holographic nature of black holes may hold the key to resolving the information paradox. As Hawking radiation carries energy away from the black hole, the event horizon gradually shrinks, but the information encoded upon it doesn't disappear. It becomes more densely packed, like an infinite library where the shelves grow closer together as the building contracts. When the black hole finally evaporates completely, the information may be released back into the universe in some as yet unknown form, perhaps through subtle correlations in the Hawking radiation itself. The universe, it seems, keeps perfect accounting records even in the face of apparent annihilation. The implications ripple outward like gravitational waves. If black holes obey this holographic principle, might the entire universe? Some physicists speculate that we may all be living inside a cosmic hologram, where the three-dimensional reality we experience is actually projected from information stored on some distant two-dimensional boundary of the cosmos. The atoms that make up your body, the neurons firing in your brain as you contemplate these ideas, all might ultimately be manifestations of information written on the surface of space-time at the edge of the observable universe. As we drift deeper into the black hole's gravitational embrace, time itself begins to behave strangely. From an outside observer's perspective, an object falling toward the event horizon appears to slow down, its image reddening and dimming as time dilation effects become extreme. But from the falling object's perspective, the crossing happens normally, while the external universe appears to speed up in a dizzying cosmic fast-forward. Near the singularity, these effects become so pronounced that the very concepts of before and after may lose their meaning entirely. The orderly progression of cause and effect that governs our everyday experience could break down completely in this quantum gravitational storm. The singularity itself remains the ultimate mystery, a place where density becomes infinite, where space-time curvature becomes infinite, where all known physical laws break down. Some theories suggest the singularity might be a gateway to another universe or another part of our own. Others propose it represents a fundamental limit to knowledge itself, a cosmic censorship that prevents the paradoxes of naked singularities from infecting the rest of the universe. What's certain is that understanding what truly happens at the singularity will require a complete theory of quantum gravity, a theory that successfully marries the continuous space-time of general relativity with the discrete quantum world. As we approach this unfathomable endpoint of our journey, we find comfort in the holographic principle's suggestion that information, the essence of all that fell into the black hole, is never truly lost. The universe appears to preserve it with perfect fidelity, even in the face of such extreme physics. This realization hints at a deeper unity underlying reality, a connection between the quantum and the cosmic that we're only beginning to glimpse. The black hole, that darkest of cosmic phenomena, may ultimately be our brightest beacon in the search for a unified understanding of physical reality. Let us rest here for now, suspended in thought at the edge of the singularity, contemplating how these quantum revelations might illuminate not just black holes, but the fundamental nature of reality itself. In our exploration, we'll examine how black holes might be connected across the universe through quantum entanglement, forming a vast cosmic network that could underlie the very structure of space-time. As we hover at the precipice of the singularity, our minds struggling to comprehend the infinite curvature of space-time, a new revelation emerges from the quantum depths. Black holes may not be isolated cosmic anomalies, but interconnected nodes in a vast celestial network. This is the realm of quantum entanglement, where particles separated by light years remain mysteriously connected, their fates intertwined regardless of distance. When we apply this quantum phenomenon to black holes, we uncovered the startling possibility that these gravitational behemoths might be linked across the universe through wormholes, Einstein-Rosen bridges, woven from the fabric of space-time itself. Imagine two black holes born from the same collapsing star or formed in close proximity during the early universe. According to quantum theory, their internal states could become entangled, creating a connection that persists even if the black holes drift billions of light years apart. This entanglement might physically manifest as microscopic wormholes, tunnels through space-time so narrow that only quantum information could pass through. The mathematics suggest these wormholes would be incredibly unstable, snapping shut in fractions of a second unless somehow stabilized by negative energy or other exotic phenomena. Yet their fleeting existence hints at a profound truth. The quantum connections between black holes could form the hidden scaffolding of the cosmos itself. This concept leads us to ER equals EPR conjecture, a daring proposal that links entanglement, EPR, with wormholes. It suggests that whenever two particles become quantum entangled, a microscopic wormhole connects them, not through conventional space, but through some deeper, more fundamental layer of reality. For black holes, this implies that their event horizons might be quantum entangled on a massive scale, creating a cosmic web of hidden connections. The fabric of space-time we observe could be like the surface of a vast ocean, while these quantum entanglements form invisible currents beneath the surface, shaping the large-scale structure of the universe in ways we're only beginning to understand. The implications ripple outward like gravitational waves through space-time. If black holes are indeed connected through quantum entanglement, it could explain how information escapes evaporating black holes, not by radiating outward through ordinary space, but by traveling through these microscopic wormholes to other points in the universe. This would preserve quantum information without violating any physical laws, neatly resolving the information paradox while revealing space-time's intrinsic interconnectedness. The event horizon's holographic nature and these quantum connections might be two aspects of the same deeper reality, like different perspectives on a multidimensional object we can't yet fully visualize. As we contemplate this cosmic web of entangled black holes, we begin to see the universe in a new light. The supermassive black holes at the centers of galaxies might not be isolated monsters, but participants in an immense quantum network that has been growing and evolving since the Big Bang. Their mergers, those catastrophic collisions that send gravitational waves rippling through space-time, could be reshaping this hidden architecture, creating new quantum connections while severing others. The universe's large-scale structure, the great cosmic web of galaxies and voids, might ultimately trace back to this underlying quantum network of entangled black holes and wormholes. Yet, mysteries remain. How exactly does quantum information traverse these connections? Could macroscopic wormholes ever become stable enough for matter to pass through? And most profound of all, if space-time itself emerges from quantum entanglement, as some theories suggest, then black holes might not just be objects within space-time, but the very looms on which space-time is woven. Each black hole's event horizon, with its perfectly encoded holographic information, could be a stitch in the fabric of reality, connecting the quantum scale to the cosmic through threads of entanglement we're only beginning to discern. As we prepare to explore how these quantum revelations might lead us to a unified theory of physics, let us linger a moment longer in this vision of interconnected black holes. The universe appears before us not as a collection of separate objects in empty space, but as a dynamic network of quantum relationships, a cosmic neural network where black holes serve as both nodes and connections, where space-time itself may be a secondary manifestation of deeper quantum connections. In this light, every black hole becomes a doorway not just to gravitational extremes, but to understanding how the universe maintains its quantum coherence across vast distances and timescales. Our journey continues as we see how these insights from black hole physics might help bridge the gap between quantum mechanics and general relativity, bringing us closer to the long-sought theory of quantum gravity. The answers may lie in the subtle interplay between entanglement and geometry, between information and space-time, a symphony of cosmic proportions playing out in the darkness between the stars. In the silent cathedral of the cosmos, where black holes stand as both priests and portals to the universe's deepest mysteries, we find ourselves at the precipice of a revelation that could unite the two great pillars of modern physics, quantum mechanics and general relativity, into a single, harmonious theory of quantum gravity. This is not merely an academic exercise, but a fundamental reimagining of reality's fabric, where the smooth, geometric curves of space-time described by Einstein emerge from the frenetic quantum dance of particles at the smallest scales. Black holes, those perfect crucibles of extreme physics, serve as our guides through this conceptual labyrinth. Their very existence demand that we reconcile the continuous with the discrete, the deterministic with the probabilistic, the cosmic with the quantum. To understand how black holes illuminate the path to quantum gravity, we must first appreciate the nature of the conflict between our current theories. General relativity paints space-time as a smooth, flexible fabric that curves in response to matter and energy, a beautifully intuitive picture that explains everything from the orbit of planets to the bending of light around massive galaxies. Quantum mechanics, on the other hand, describes a world of discrete packets of energy, of particles that can be in multiple places at once until measured, of fundamental uncertainties woven into the fabric of reality at microscopic scales. These two frameworks work spectacularly well in their respective domains, but when brought together, particularly in the extreme environment of a black hole, they produce nonsensical results like infinite densities at singularities and the paradoxical loss of quantum information. The quest for quantum gravity is essentially the search for a deeper language that can describe both regimes simultaneously, and black holes serve as Rosetta Stones for this translation. Their event horizons represent boundaries where quantum effects become significant on macroscopic scales, while their interiors push matter and energy to such extremes that quantum gravitational effects must dominate. Several approaches have emerged in this grand theoretical pursuit, each offering unique insights into how spacetime might behave when viewed through a quantum lens. String theory, perhaps the most well-known candidate for quantum gravity, proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings, each different vibrational mode corresponding to different particles and forces. In this framework, what we perceive as a black hole's singularity would be replaced by an incredibly dense fuzzball of strings vibrating at their maximum possible energy. This fuzzball would have finite size, avoiding the infinities predicted by classical general relativity, while preserving all quantum information within its complex stringy structure. The event horizon becomes less a point of no return and more a transition zone where strings become highly excited, creating a quantum firewall that scrambles information but doesn't destroy it. Remarkably, string theory naturally incorporates the holographic principle, the idea that information in a volume of space can be encoded on its boundary, which mathematically connects string theory in higher dimensional spaces to quantum field theories on their boundaries. Loop quantum gravity takes a different but equally fascinating approach by quantizing space-time itself. In this framework, space is composed of discrete, interconnected loops that form a spin network, a kind of quantum foam that gives rise to the smooth space-time we experience at larger scales. When applied to black holes, loop quantum gravity suggests that the singularity is replaced by a quantum bounce, a point where collapsing matter reaches maximum density and then rebounds, potentially creating a white hole that spews matter back out into another region of space-time. This leads to the startling possibility that what we call a black hole might actually be a tunnel to another universe or another part of our own, with the event horizon marking the transition between inward and outward flow. The theory also provides a microscopic explanation for black hole entropy by counting the number of quantum states that can produce a given horizon area. Causal dynamical triangulations offer yet another perspective, modeling space-time as being built from tiny four-dimensional triangular blocks that combine to form the larger structure of the universe. Computer simulations using this approach show that at extremely small scales, space-time becomes fractal and chaotic, but at larger scales, it smooths out into the four-dimensional continuum we recognize. When applied to black holes, this suggests that near the singularity, the very dimensionality of space-time might change, perhaps collapsing to two dimensions or fluctuating wildly between different dimensional configurations. The holographic principle, which we've encountered before, takes on profound significance in these quantum gravity theories. It posits that all the information contained within a volume of space, including the three-dimensional arrangement of matter and energy, can be represented as encoded information on that volume's two-dimensional boundary. Black holes, with their perfect correspondence between surface area and entropy, provide compelling evidence for this principle. The event horizon surface area, measured in Planck units, appears to directly count the number of fundamental degrees of freedom, the basic yes-no questions we can ask about the black hole's quantum state. This realization has led to the radical notion that what we perceive as three-dimensional reality might be a projection from information processing happening at the universe's boundaries, a cosmic version of how a hologram creates a three-dimensional image from two-dimensional film. As these theories converge, several profound insights emerge about the nature of quantum gravity. First, space-time itself appears to be emergent rather than fundamental, a secondary phenomenon that arises from more basic quantum interactions, much like temperature emerges from the motion of molecules. Second, information seems to play a primary role in shaping physical reality, with black holes serving as ideal systems for studying information geometry correspondences. Third, the distinction between matter and space-time blurs at quantum gravitational scales. What we perceive as particles might simply be particular configurations of space-time's quantum structure. The implications for black hole physics are revolutionary. The information paradox dissolves when we realize that quantum information is never truly lost. It may be scrambled and spread across the event horizon, or it may tunnel through quantum connections to other regions of space-time. Hawking radiation transforms from random thermal noise into a complex quantum signal carrying encrypted information about everything that fell into the black hole. Even our concepts of time undergo radical revision. The smooth flow we experience may emerge from more fundamental timeless quantum correlations, much like the apparent motion of a movie emerges from static frames. Remarkably, these theoretical advances are beginning to suggest experimental tests. The Event Horizon Telescope's images of black hole shadows could reveal subtle signatures of quantum structure at event horizons. Precise measurements of gravitational waves from merging black holes might show deviations from classical predictions that reveal quantum gravitational effects. Laboratory experiments using ultra-cold atoms or optical systems can create analog black holes that mimic quantum gravitational phenomena. Even the cosmic microwave background might contain faint imprints from quantum gravitational processes in the early universe. As we stand at this threshold of understanding, we realize that black holes have been whispering the secrets of quantum gravity to us all along. Their event horizons demonstrate the deep connection between information and space-time geometry. Their singularities, or lack thereof, show us where classical physics breaks down and quantum effects take over. Their Hawking radiation reveals how quantum fluctuations can have macroscopic consequences, and their potential quantum connections with other black holes through entanglement and wormholes hint at a universe where space-time itself is secondary to an underlying network of quantum relationships. Our journey now turns toward the cosmic consequences of these revelations. If space-time is indeed emergent from quantum information processing, what does that mean for the origin and fate of the universe? Could the Big Bang itself have been a kind of quantum gravitational phase transition? Might the universe's accelerating expansion be related to quantum information spreading across its boundaries? And most profoundly, if black holes are teaching us about the quantum structure of space-time, could they also be the key to understanding consciousness, dark energy, or other great mysteries of existence? The answers to these questions may lie in the subtle interplay between quantum information and space-time geometry, a symphony playing out on scales from the Planck length to the cosmic horizon, with black holes serving as both instruments and conductors in this grand cosmic orchestra. We'll see how these quantum gravitational insights are revolutionizing our understanding of cosmology, particle physics, and perhaps even the nature of reality itself. Beneath the velvet darkness of the event horizon, where time itself stretches and warps like molten glass, black holes transform into nature's ultimate laboratories, testing grounds where the universe experiments with its own fundamental laws. These gravitational leviathans are not merely objects in space, but dynamic interfaces where the quantum and cosmic realms perform an intricate pas de deux, revealing secrets about reality that we could never discover in earthbound laboratories. As we peer deeper into this quantum crucible, we begin to see how black holes may hold the keys to understanding not just gravity, but the very nature of existence itself. The quantum behavior of black holes manifests most strikingly in their thermal properties, a revelation that forever changed our understanding of these cosmic phenomena. When Stephen Hawking first calculated that black holes should emit radiation with a perfect thermal spectrum, it created a profound paradox. Quantum field theory in curved spacetime predicts that this Hawking radiation emerges from the quantum vacuum fluctuations near the event horizon, with particle-antiparticle pairs being torn apart by the black hole's immense gravitational field. The temperature of this radiation is inversely proportional to the black hole's mass. A microscopic black hole would glow fiercely at billions of degrees, while a supermassive black hole like M87 would emit barely perceptible whispers at trillionths of a degree above absolute zero. This thermal behavior connects black holes to thermodynamics in startling ways. The event horizon's surface area corresponds to entropy, a measure of the black hole's internal quantum states, while the surface gravity at the horizon relates to temperature. These connections suggest that black holes are not just gravitational objects, but fully fledged thermodynamic systems, obeying the laws of physics we know from studying heat and energy. The holographic principle takes this further, indicating that all the information about the black hole's interior is encoded on its two-dimensional surface, much like a computer's three-dimensional operations can be represented by two-dimensional circuitry. As we examine these quantum thermodynamic properties more closely, we encounter the black hole information paradox in its most acute form. If a black hole evaporates completely through Hawking radiation, what happens to all the quantum information about the matter that fell in? Quantum mechanics insists that information cannot be destroyed. It must be preserved, even if it's scrambled beyond recognition. Yet, general relativity suggests that this information disappears forever behind the event horizon. Resolving this paradox has led physicists to revolutionary ideas about how information might be preserved, perhaps through subtle correlations in the Hawking radiation, or via quantum entanglement between the black hole's interior and exterior, or through wormhole connections to other regions of spacetime. Recent advances in quantum information theory have shed new light on this puzzle. The concept of quantum error correction, the same principle that allows quantum computers to protect information from decoherence, appears naturally in black hole physics. The information swallowed by a black hole may not be localized at any particular point, but rather spread non-locally across the entire event horizon in a highly entangled state. This quantum hair would allow information to escape gradually as the black hole evaporates, resolving the paradox while maintaining consistency with both quantum mechanics and general relativity. The event horizon thus becomes a kind of quantum processor, performing the most complex computations imaginable as it encodes and transforms information. The quantum nature of black holes also reveals itself in their rotational properties. A spinning black hole, described by the Kerr solution in general relativity, develops an ergosphere around its event horizon, where spacetime itself is dragged around at relativistic speeds. In this region, quantum field theory predicts remarkable effects like superradiance, where waves scattering off the black hole can extract rotational energy and emerge amplified. This process creates quantum mirrors around rotating black holes that can produce spontaneous particle creation, effectively turning the black hole's rotational energy into detectable quantum emissions. Perhaps most astonishingly, black holes may provide experimental access to quantum gravity phenomena through their gravitational wave signatures. The Laser Interferometer Gravitational Wave Observatory has detected numerous black hole mergers, each event producing ripples in space-time that carry information about the object's properties. As our detectors become more sensitive, we may discern subtle deviations from classical predictions that reveal quantum structure at event horizons, perhaps echoes of the quantum gravitational regime near what we used to call singularities. The final moments of black hole mergers, when quantum gravitational effects should dominate, could provide our first observational window into the quantum nature of space-time itself. Laboratory experiments are now attempting to recreate black hole quantum phenomena using analog systems. Bose-Einstein condensates can simulate event horizons where sound waves behave like light near a black hole. Nonlinear optical materials create optical black holes that trap light in ways mimicking gravitational trapping. Even flowing water can model black hole dynamics, with surface waves representing quantum fields near horizons. These analog systems allow us to test ideas about Hawking radiation, information scrambling, and other quantum gravitational effects in controlled settings, providing crucial insights while we wait for astronomical observations to catch up with theory. As we stand at this crossroads between theory and observation, between the quantum and cosmic scales, black holes emerge not as endpoints of understanding, but as gateways to new physics. Their quantum properties challenge us to rethink fundamental concepts. Is space-time truly fundamental, or does it emerge from more basic quantum information processing? How does the unitary evolution of quantum mechanics reconcile with the apparent non-unitarity of black hole evaporation? Could the quantum entanglement structure of black holes teach us about the entanglement underlying space-time itself? Might the resolution of black hole paradoxes lead us to a deeper theory that unifies all physical laws? The answers to these questions may come from continued observations of real black holes across the electromagnetic and gravitational wave spectra. They may emerge from quantum computer simulations of black hole dynamics, or they might arise from theoretical breakthroughs that finally reconcile the quantum and gravitational realms. What's certain is that black holes, those darkest of cosmic objects, are illuminating the path toward understanding reality's deepest nature in ways we're only beginning to comprehend. As we prepare to explore how these quantum revelations might transform our understanding of the universe's origin and fate, we carry with us the profound realization that black holes are not merely celestial curiosities, but active participants in shaping the quantum architecture of reality. Their event horizons are not just boundaries in space, but frontiers of knowledge where the next revolution in physics awaits discovery. In their perfect darkness, we may yet find the brightest illumination of nature's fundamental truths. As we trace the quantum whispers of black holes back through the arrow of time, we arrive at the most profound revelation of all. These gravitational behemoths may hold the key to understanding the very origin of space-time itself. The universe's first moments after the Big Bang, when all existence was compressed into a volume smaller than an atom, represent conditions strikingly similar to those inside a black hole's event horizon. This cosmic symmetry suggests that black holes are not merely products of the universe, but potential progenitors, that the birth of new universes may occur within their quantum gravitational depths, and that our entire cosmos might itself have emerged from such a singularity. The mathematics of quantum gravity paints a startling picture of black holes as cosmic wombs. When we apply loop quantum gravity's equations to the extreme conditions near a singularity, they predict a bounce, a quantum repulsive force that halts infinite collapse and triggers expansion. This suggests that what appears as a black hole in our universe could transform, in its deepest quantum gravitational realm, into a white hole spewing matter into a new spacetime. The event horizon becomes not an endpoint, but a bridge between universes, a Einstein-Rosen wormhole sustained by quantum effects that prevent its collapse. Through this looking glass, the death of stars in our cosmos could give birth to entirely new universes, with their own physical constants and dimensions. This concept of cosmological natural selection, proposed by physicist Lee Smolin, imagines black holes as Darwinian selectors of physical laws. Each new universe born within a black hole might have slightly different fundamental constants than its parent universe. Those universes whose constants produce more black holes would have more offspring, explaining why our universe appears fine-tuned for black hole production. The quantum gravitational processes at black hole singularities thus become the mechanisms of cosmic evolution, with black holes serving as portals through which the multiverse explores different physical laws. The holographic principle takes on cosmic significance in this context. If our three-dimensional universe is indeed a projection from information encoded on a two-dimensional surface at infinity, then black holes represent localized versions of this phenomenon, their interiors projected from information on their event horizons. This stunning parallel suggests that the entire universe might operate on the same informational principles we observe in black holes, just at vastly different scales. The quantum entanglement that connects particles across black hole horizons might be the same phenomenon that established correlations across our observable universe during inflation, a cosmic web of quantum connections stretching back to creation itself. Remarkably, these ideas find support in the cosmic microwave background. The temperature fluctuations in this afterglow of the Big Bang show patterns that some theorists interpret as evidence of a pre-Big Bang universe. Certain anomalous features in the CMB, like the famous cold spot, could potentially be explained by quantum gravitational effects imprinted on our universe from its parent cosmos. If true, this would mean that black holes preserve and transmit quantum information not just across space, but across universes. That their singularities are not endpoints, but transformation points in an endless cycle of cosmic death and rebirth. The quantum behavior of primordial black holes adds another layer to the story. These hypothetical black holes, potentially formed from density fluctuations in the early universe, could have evaporated by now through Hawking radiation. Their final moments would have been spectacular bursts of high-energy particles carrying quantum information about the early universe's conditions. Some theories suggest these evaporation events might have left detectable imprints in the CMB or in the distribution of matter throughout the cosmos. Others propose that some primordial black holes might have survived to today, hiding as dark matter candidates, their quantum gravitational interiors possibly containing relics of the universe's first moments. As we push our understanding back to the Planck epoch, the first 10 to the -43 seconds after the Big Bang, black hole physics becomes indistinguishable from cosmology. At these energies, quantum fluctuations in space-time itself would have been significant, potentially creating a foam-like structure of virtual black holes and wormholes. The transition from this quantum foam to the smooth space-time we observe today might have been a phase transition analogous to water freezing into ice, with black holes representing defects or boundaries between different space-time phases. In this view, the expansion of the universe emerges naturally from the quantum dynamics of space-time itself, with inflation driven by the same repulsive quantum forces that prevent singularities from forming in loop quantum gravity. The implications for time's arrow are profound. While general relativity treats time as just another dimension, quantum mechanics insists on a fundamental difference between space and time through the concept of measurement and wave function collapse. Black holes, sitting at the intersection of these theories, suggest that the flow of time itself may be an emergent property of quantum entanglement. As matter falls toward a black hole, from an outside observer's perspective, it appears to freeze at the event horizon, its information gradually transferred to the horizon's quantum degrees of freedom. This mirrors what quantum gravity suggests happened during the Big Bang.
that what we perceive as the beginning of time was actually the emergence of time from timeless quantum correlations.
Current research is exploring how these ideas might be tested. Precision measurements of the CMB could reveal patterns imprinted by quantum gravitational processes in the early universe. Gravitational wave detectors might someday detect echoes from the quantum structure of black hole horizons. Tabletop experiments with quantum materials could simulate the conditions of the early universe, allowing us to study cosmic genesis in the lab. And theoretical work continues to refine our understanding of how quantum information, space-time geometry, and thermodynamics intertwine at the most fundamental levels. As we stand at this frontier of knowledge, we realize that black holes have been guiding us toward a new understanding of cosmic origins all along. Their event horizons mirror the Big Bang's apparent horizon. Their quantum information processing resembles the universe's own holographic nature. Their singularities may be not endings, but beginnings. In this grand vision, black holes are not just inhabitants of our universe, they are its inheritors and progenitors, the means by which the cosmos reproduces and evolves, the crucibles where space-time itself is continually reborn from quantum chaos into classical order. Our journey now turns toward the future, where we'll explore how these quantum gravitational principles might shape the ultimate fate of the universe, and whether black holes will have the final word in the cosmic story. Will they evaporate into nothingness or seed new universes? Is our cosmos destined for heat death, or is there a quantum gravitational mechanism for cosmic rebirth? The answers, as we'll see, may lie in understanding black holes not just as objects in space, but as the fundamental architects of space-time itself. As we gaze across the cosmological horizon toward the universe's twilight, we find black holes standing as both sentinels of entropy and potential architects of cosmic renewal. In these final epochs, when stars have burned out and galaxies have dissolved into darkness, black holes will become the universe's dominant structures, their quantum gravitational properties determining whether existence culminates in eternal silence or cycles toward rebirth. The story of the far future is written in the quantum mechanics of these last surviving entities whose slow evaporation may represent either the universe's final exhalation or the seeds of new creation. The quantum destiny of black holes unfolds against the backdrop of an expanding cosmos dominated by dark energy. Over timescales that dwarf the current age of the universe, measured not in billions, but in googles of years, black holes will gradually evaporate through Hawking radiation. A solar mass black hole requires approximately 10 to the power 67 years to dissipate completely, while supermassive black holes at galactic centers may persist for many, many years or longer. During this inconceivably prolonged evaporation, each black hole becomes a quantum gravitational laboratory operating in slow motion, its final moments potentially revealing truths about reality that are currently hidden by the universe's relative youth. As a black hole nears the end of its evaporation, quantum gravitational effects become increasingly significant. The semi-classical approximation, where quantum fields propagate on curved spacetime, breaks down when the black hole's mass approaches the Planck scale, about 22 micrograms. At this critical point, the full theory of quantum gravity must take over, potentially transforming the evaporating remnant into something far stranger than a mere vanishing point of energy. Some theories suggest the formation of a stable Planck star remnant, an ultra-dense quantum gravitational object that preserves information without maintaining an event horizon. Others propose that the black hole's complete evaporation leaves behind a topological feature of spacetime, a wormhole mouth, or a region of spacetime with different fundamental constants. The information paradox reaches its climax in these final moments. If Hawking radiation carries away all information about what fell into the black hole, encoded in subtle quantum correlations, then the evaporation process must become highly non-thermal at the endpoint.
The radiation spectrum would shift from perfect thermal equilibrium to a state carrying the quantum fingerprints of everything the black hole ever consumed. This transition might produce distinctive signals, perhaps bursts of high-energy particles or distortions in the fabric of spacetime, that could theoretically be detected by civilizations existing in that distant epoch. Remarkably, these far-future quantum gravitational processes may create conditions resembling the early universe. The extreme energies and densities during a black hole's final evaporation could trigger spontaneous symmetry breaking, potentially resetting physical constants or even space-time dimensionality in localized regions. If such regions then inflate into new universes, as suggested by theories of black hole cosmology, then each evaporating black hole could become the Big Bang of a new cosmic epoch. In this scenario, the multiverse grows fractal-like, with black holes birthing new universes whose black holes birth further universes in an endless cascade of creation. The ultimate fate of information in this cosmic drama depends on the exact mechanism of black hole evaporation. In some models, information remains forever trapped in Planck-scale remnants. Others suggest it's radiated away in the final burst of evaporation. The most radical proposals claim information escapes into baby universes through quantum gravitational tunnels, meaning our own universe might contain information from its parent black hole in another cosmos. This leads to the mind-bending possibility that the fundamental constants and laws of our universe were selected by quantum processes inside a black hole belonging to a previous cosmic cycle. The geometry of space-time in these final epochs becomes increasingly dominated by quantum effects. As black holes evaporate, the universe approaches absolute zero temperature, but quantum fluctuations ensure it never becomes completely static. Virtual black holes may spontaneously form and evaporate in the quantum foam, creating ephemeral bridges between distant regions of space-time. On cosmological scales, the combination of dark energy's accelerated expansion and black hole evaporation produces a universe that grows both emptier and more quantum in character, eventually consisting mostly of Hawking radiation, slowly redshifting toward oblivion. Yet, even in the seemingly bleak future, quantum mechanics may provide pathways for renewal. The same quantum tunneling effects that allow particle emission from black holes could enable more dramatic transitions on cosmic scales. Given sufficient time, measured not in years but in exponential powers of years, quantum fluctuations could theoretically trigger a new inflationary epoch, restarting the cosmic cycle. In this view, black holes serve as cosmic capacitors, storing and eventually releasing the potential energy needed for universal rebirth through their quantum gravitational dynamics. Current research is exploring how to test these far-future scenarios through observations in our cosmic present. The evaporation of microscopic black holes, if they exist, could provide snapshots of the universe's final moments. Precision measurements of Hawking radiation's quantum correlations might reveal information recovery mechanisms. Even the cosmic microwave background could contain subtle imprints from quantum gravitational processes in the early universe that hint at how space-time behaves in the extreme far future. As we contemplate this quantum gravitational eschatology, black holes transform from destroyers to potential redeemers in the cosmic narrative. Their quantum properties suggest that the universe's fate may not be a simple progression from order to disorder, but a more nuanced dance where entropy and information, gravity and quantum mechanics, death and rebirth are eternally intertwined. The final word of existence may not be heat death, but transformation, with black holes serving as the alchemists that convert a dying universe's remains into the raw materials for new creation. Our journey through the quantum landscape of black holes thus comes full circle, from their role in cosmic origins to their potential part in universal rebirth. In their perfect darkness, we have found illumination. In their apparent simplicity, infinite complexity. In their destructive power, creative potential. We're left with the profound realization that black holes are not just objects in the universe, they are the universe's way of probing its own deepest nature. Quantum laboratories where space-time itself experiments with its fundamental architecture. The final theory of quantum gravity, when discovered, may reveal that black holes were the teachers we needed all along to understand reality's most sacred mysteries. As our journey through the quantum landscape of black holes draws towards its contemplative close, we arrive at a revelation that transcends astrophysics and ventures into metaphysics, that these gravitational marvels may represent the fundamental stitches in the fabric of existence itself. The deeper we probe their quantum mysteries, the more black holes appear not as anomalies in the universe, but as essential manifestations of its underlying structure. In their perfect darkness, we find illumination about the most profound questions of reality, consciousness, and the nature of existence. The quantum principles we've discovered governing black holes, holography, entanglement, information preservation, are now being recognized as potentially universal features of reality. The holographic principle, first glimpsed in black hole thermodynamics, suggests that all the information in a volume of space might be encoded on its boundary.
Applied universally, this implies our three-dimensional experience could be a projection from information processing happening at the cosmic horizon. The quantum entanglement that connects particles across black hole event horizons may be the same phenomenon that establishes quantum coherence throughout the universe. Even Hawking radiation's information paradox resolution hints that information preservation could be a fundamental feature of existence, not just a property of black holes. This perspective transforms how we view black holes' role in the cosmos. Rather than cosmic vacuum cleaners, they emerge as dynamic nodes in the universe's quantum information network, processing, transforming, and preserving information according to precise mathematical rules. Their event horizons are not mere boundaries, but active membranes where space-time and quantum information interact in complex ways we're just beginning to decipher. The black hole's interior becomes a quantum circuit where information is neither created nor destroyed, but eternally processed and preserved. The implications ripple outward to touch some of humanity's deepest philosophical questions. If black holes preserve information perfectly, does this suggest the universe fundamentally remembers everything that happens within it? Does the holographic principle imply that reality is fundamentally informational, that the stuff of the universe is not matter or energy, but bits of quantum information? The quantum gravitational behavior of black holes seems to be whispering yes to these profound possibilities, hinting at a reality far stranger and more magnificent than our classical intuitions suggest. Even our understanding of consciousness may need to expand in light of these quantum gravitational insights. The brain's neural networks bear striking mathematical similarities to the quantum entanglement networks that may underlie space-time itself. Some theorists speculate that consciousness could be a quantum gravitational phenomenon, that the very act of observation that collapses quantum wave functions might involve subtle space-time curvature effects operating at the Planck scale. If true, this would mean black holes are not just objects out there, but that their quantum gravitational principles operate at every scale, including within the human mind. The emerging picture suggests that black holes are not exceptions to cosmic rules, but concentrated examples of reality's deepest principles. What we observe in their extreme environments, information preservation, holographic encoding, quantum entanglement, appears to be true everywhere, just more easily visible where gravity and quantum mechanics collide most violently. This realization is guiding physicists toward a new paradigm where space-time emerges from quantum information processing, with black holes serving as the clearest windows into this deeper reality.
As we stand at this frontier of understanding, we find black holes have become our most profound teachers. They've shown us that information may be more fundamental than matter or energy, that space-time is likely emergent rather than primary, quantum entanglement could underlie cosmic structure, and the universe appears to preserve all information perfectly. Reality may be holographic in nature, too. These lessons from the darkness are reshaping not just physics, but our very conception of existence. The once mysterious black hole now stands revealed as a key to understanding reality's deepest architecture, a cosmic Rosetta Stone, translating between the quantum and gravitational realms. As our exploration nears the end, we're left with a sense of awe at how these perfect manifestations of gravity's triumph have become portals to quantum revelation. The journey from viewing black holes as cosmic oddities to recognizing them as essential expressions of nature's deepest truths represents one of science's most profound paradigm shifts. In their event horizons, we find the meeting point of all physics. In their quantum whispers, we hear hints of a grand unified theory. In their paradoxical nature, we discover the contours of reality's fundamental structure. The universe, it seems, has been hiding its greatest secrets in plain sight, in the perfect darkness of black holes, where gravity and quantum mechanics dance their eternal dance, weaving the tapestry of existence one quantum thread at a time. Our understanding remains incomplete, but the path forward is clear. To comprehend reality at its deepest level, we must continue listening to what black holes' quantum whispers are telling us about the fundamental nature of existence itself. As we bring our journey through the quantum mysteries of black holes to a gentle close, let us linger for a moment in the profound stillness of the cosmic dark, where the gravitational embrace of these celestial wonders merges with the whispering dance of quantum particles. From the event horizon's shimmering boundary to the unfathomable depths of the singularity, from the holographic encoding of information to the entangled webs connecting black holes across spacetime, we have wandered through a landscape where the fundamental nature of reality reveals itself in quiet, breathtaking beauty. Our voyage began at the edge of a black hole's event horizon, where the quantum vacuum thrums with virtual particles, and Hawking radiation slowly carries whispers of the black hole's secrets back into the universe. We witnessed how these gravitational giants are not merely consumers of matter and light, but participants in a delicate quantum ballet, where particles born from the fabric of space-time itself are torn apart by gravity's inexorable pull, leaving behind subtle imprints of all they have consumed. Venturing deeper, we explored the holographic principle, discovering how black holes encode the three-dimensional information of everything that falls within them onto their two-dimensional surfaces, a revelation that suggests our entire universe might operate on similar principles. The quantum entanglement connecting particles across the void mirrored the strange non-locality that may underlie all of space-time, hinting that black holes are not isolated phenomena, but nodes in a vast cosmic network of quantum connections. We stood at the precipice of singularities, where the known laws of physics dissolve into the unknown, and contemplated how black holes might be bridges to other universes or cosmic rebirths. The information paradox, that eternal question of whether knowledge is truly lost in a black hole, led us to profound realizations about the universe's perfect memory, its insistence on preserving every bit of information, scrambled though it may be in the quantum tumult of the event horizon. Through the lens of string theory, loop quantum gravity, and holography, we saw how black holes force us to reconcile the vast and the infinitesimal, proving that space-time itself may be emergent, a secondary phenomenon rising from deeper quantum interactions. These gravitational behemoths, once thought to be the universe's ultimate endpoints, revealed themselves instead as potential creators, seeds of new universes, laboratories of quantum gravity, and perhaps even the architects of cosmic evolution. As we contemplate the far future, we saw how black holes will outlast stars and galaxies, their slow evaporation through Hawking radiation carrying them toward a final quantum transition, one that may spark new cosmic beginnings even as our own universe grows cold and dark. The realization that black holes could be both the universe's final sentinels and the midwives of new creations fills the cosmic scale with a profound cyclical poetry. Now, as our journey concludes, let us reflect on the deeper harmony we've uncovered. Black holes teach us that darkness is not absence, but a different kind of fullness, that entropy is not merely chaos, but information waiting to be decoded, that even the most destructive forces in the cosmos may be creative in ways we are only beginning to understand. They show us a universe where gravity and quantum mechanics, once thought irreconcilable, are in fact partners in an ancient, eternal dance, one that plays out in the warping of space-time, the entanglement of particles, and the holographic preservation of every event, every atom, every moment that ever was. As you drift away from these revelations, carried on the gentle tide of this cosmic lullaby, remember that the mysteries we've explored are not distant abstractions. The same quantum principles that govern black holes, entanglement, superposition, the holographic nature of information, operate all around us and within us. We are made of stardust that once swirled near these gravitational maestros, our atoms forged in their violent surroundings. In a very real sense, we are the universe contemplating itself, our minds perhaps even touching upon the same quantum gravitational phenomena that shape black holes and space-time itself. In this quiet moment of cosmic contemplation, we find ourselves at the threshold between waking and dreaming, between knowledge and wonder. The black holes we've journeyed with today, those perfect spheres of darkness that warp space and time, are not just astronomical phenomena, but mirrors reflecting back our deepest questions about existence. They show us that destruction and creation are two faces of the same cosmic coin, that endings are woven seamlessly into beginnings, and that the universe keeps perfect accounting of all that transpires within it. Their silent song is one of transformation, reminding us that even in the deepest darkness, the potential for new light always exists. So let us take one final look at these gravitational wonders before sleep carries us away. See them now not as cosmic anomalies, but natural expressions of a universe far wiser and more mysterious than we ever imagined. Their evident horizons mark not endings, but transitions. Their singularities not termini, but gateways. As you surrender to sleep tonight, imagine yourself gently orbiting a black hole's evident horizon, safely suspended in the perfect equilibrium between its gravitational pull and your own momentum, a metaphor for the delicate equilibrium between consciousness and dreams, between knowing and mystery.
So rest now, cradled in the knowledge that you float in a universe far stranger and more magnificent than we could have imagined. A universe where black holes sing quantum lullabies across the eons, where darkness holds as much wonder as light, and where every ending, should we look closely enough, may simply be a new beginning in disguise. Sleep well, dream deep, and may the quiet majesty of black holes and their quantum secrets linger in your thoughts like starlight on still water, gentle, eternal, and full of infinite possibility. Good night.